Stay with me. I told him it was all up to him. All right. So how do you actually, so I do have to do this on boards. We're going to skip that. But those who have in the class today still have to do the work.
We skip questions now.
No, not that stuff. I need you to understand. But you don't have to do the work on the board. Okay? So here's the thing. Is that the work on the board you're supposed to do? Put this down. So, where does this come from? Yeah, you got this. Where does this come from? How did I get h of x of t? Which was that formula that I had right up here. So what? How do I get this all to be in terms of t?
Well, you take the t value and you plug in the RT, and then you get the values for x and y and plug it in.
Perfect answer. So this thing here came from taking that x of t, which was t, substituting it in, the y of t, which was t squared over 20, plugging that in for y, and you'll get this formula. You also have to do the offset. That picture is great. So the offset is I have an arc length. And so where does that arc length come from? It's taking the x of t and y of t, calculating the derivative like you did earlier. So this gives you the derivative of x of t, y of t from the original parameterized form. And then, yes?
Is that like a partial derivative?
No, it's not. It's an actual x prime. So up here, the x of t is t. X prime is 1. So it's not a partial derivative. It's only with respect to t. Okay. And then the derivative with respect to y is going to be 2 times t.
So are we deriving, which equation are we deriving?
You're doing the magnitude of the arc length. So what, somebody had said, I think you were saying, if you pull this straight, the distance has changed, right? It's because it's a curve. So if I really want to know the distance traveled over this curve, I'm going to have to calculate the arc length. It's coming there. So let me go down. So so I have this h of x. I take the t, put it in this, take the t squared, put it in that, and then find the derivative of this r of t.
Driving r of t?
I'm driving the arc length. So the arc length formula is right here. This is the arc length formula. It's the magnitude of this derivative. So I need these components to plug them in.
So we're deriving r of t to plug it.
Let me put this up on the board. So you have this r of t. It's your position vector as a function of time. You need to find the arc length. To find the arc length, step 1 is to take r prime of t, which is this. Good? And step 2, find the magnitude. So that's this. Component squared under square root. That's what I have here. This integral becomes this. Arc length factor is the new thing in here. And you need that because when you have a curve, the distance along that curve is stretched out. So what you're really doing in real life is you're pulling this straight and calculating the distance across this curve. That's what the arc length factor does. It accounts for the curve having more distance than a line.
Arc length factor is just like an equation we plug in the arc t's. So our arc length factor is the magnitude of that?
Yes.
Okay.
So the formula of, let me put it up here as just formula. If I have h of x, y, df, meaning is still the same. Over this curve, that's the notation. The formula is, it's the integral from 0 to 10, because that's the endpoint, but there's wiggle in between. So you're going to have h of x of t, y of t, found the way Sophia said, and then here you're going to put r prime of t dt. That's the formula. Yes. It is. You're changing. That's very insightful. You're taking the curve and making it a line. And this is a normalization piece that factors in that the curve has more distance on it than a line does.
So ds is equivalent to the arc length factor?
Yes.
Can you explain one more time what R of T is?
It's the position factor. Because when you're on a curve and you're walking on this hiking trail, the position tells you where you are at every time. Can you send me those pictures, Helen?
Yeah, I just.
Okay, everybody still with me? What has changed? What's different from the first integral that you did to this one?
ds.
The ds has changed. That's the big thing. You have an arc length factor. It deals for the fact that you're walking along a curve. You need to account for that extra distance because you have a curve. That's what's changed. That's all that's changed.
So you have to take the antiderivative.
Say it again?
You have to take the antiderivative of all that now? If you want to solve it.
Hopefully you don't. Because we had a lot of concept questions, right? So hopefully you don't. Because you know what? You can get something on your cell phone that does that. But it's the understanding of what it is. You want to take the derivative, you want to integrate that? Okay, so I don't want to
If we solve that, that would give you the length of the line.
it would give you the heart rate, it would give you the total load, right? So it's measuring the total load, physiological load going on that hiking trail. Right? So that's what you're measuring. One more thing, vector fields. You're with me still? Are you with me still?
What other weakness would be on that paper?
10.
Now we're getting to vector field. Vector field is like the easiest thing. The last little wrinkle I'm going to put in there. So, did anybody go running like a few days ago and there was a wind? And there's something about West Point, it doesn't matter where you are, it feels like the wind is directly at you. Yeah. Like if I walk to Arvin, the wind is at me, and if I walk back, the wind is at me. I don't know how that's possible, but it seems possible. So suppose the same soldier's walking along that same trail and there's a wind. How's that going to affect his or her load? It could increase it if the wind is at you, right? Like it feels like at West Point. Or the other way, if you're running or walking or rucking and the wind is going the same direction, then it's supposed to help you. So either the wind can hurt you or help you.